Good day, it's a pleasure to be here. IGCP is the International Geological Correlation Program. Effectively, it's a mechanism to try to get groups of researchers together to work together without giving them any money. Those researchers effectively use that collaborative framework as a mechanism to get money from whatever funding streams they themselves can address. But in the process, we're actually able to, or have been able to achieve a fair amount in terms of pulling bits and pieces together. And I'd like to have a look at some of what we learn from that, because it's probably very relevant at a smaller scale to the very much bigger scale issues around big data. This particular project within IGCP is looking at supercontinent cyclicity, and I link back into the geodynamics in the mantle as to what drives that. So it introduces a different perspective on the data sets that much of what we've heard so far in this conference doesn't necessarily address. There's a big change in time that comes with dealing with Earth time. We developed certain data systems within this project and one of the predecessor ones to allow us to compile data across national boundaries. We've hopefully learned from that. We've certainly grown those data systems way beyond what was available at national level. We're probably about 6 times more data now than any individual country's data system within the things that we were working with. But we're also looking at trying to leverage data in other pre-existing database systems. And then we're wanting to move forward into the paleogeographic plate reconstruction aspects. As I said earlier, this is a seriously minimalist version of big data. One of the things that comes out in dealing with the students and the general public community is this perception that one really starts with very disorganized data with big data. In fact, that's seldom the case. A lot of the data that one works with is actually remarkably well organized in terms of the way it feeds into systems, etc., as against just being, give me your garbage and I'll make sense of it. The big thing I'd like to bring through here, though, is that when we're dealing with a lot of earth science data, we have to look at how things vary both in space and time. And the time we're talking here is Earth time. In addition, most of the data we're working with is ultimately non-parametric. So the inferential statistics that we assume we want to work, that many people will work with, just doesn't really apply. And certainly in the mineral exploration industry side of things, the stuff we're interested in is the stuff that actually doesn't fit not the parametric type statistics. The other aspect that we are seriously ignoring, to my mind, is that most of our data has significant uncertainty. And we're not looking at representing how that uncertainty plays through into any of the derived data products. We're not visualizing that. We're not looking at the software we're not producing software that allows us to represent that. So we're actually creating a mindset in which we feed data into black boxes, and what comes out is it. We seriously need to change that mindset in terms of our training of students, etc. And the other aspect that tends to fall out in a lot of the big data type, in terms of the way big data is often presented to the community, we ignore the essential role of discipline-specific knowledge. It keeps coming in behind the scenes, but we tend to be focusing on the technologies and the processes, etc. I'd like to make a call, given that this here is within the Geological Society, that with a lot of the type of data that we've been working with is actually via the academic community, ultimately in publications. We're not teaching people, both academics and the newer generation students, how to prepare their data to facilitate exchange. Typical supplementary tables are still being presented in many cases as PDFs, certainly laid out, whether they're in spreadsheets or otherwise, as though they were publication tables. They're not created and designed to be able to read them very easily. None of the design concepts that go with normalization or how to work with importing data are being taught routinely to our students and then being applied when it comes to publishing in the journals. We're not even pushing through a need to capture longitude and latitude. My particular field of experience over the years has primarily been geochronology. At the moment, probably 80% of what gets published in journals actually comes with some sort of geographic coordinate. If you look at the geochemistry data, it's probably worse than 5%. How are we ever going to leverage that data to use it in a compiled system if we don't capture the types of information that we really need to have? And PDFs are absolutely horrible when it comes to working with data, no matter what some of the folks seem to be applying. Have you ever tried to compile data from a table when some of the columns don't have information in them? You spend more time fixing things than you might as well type it in by hand in many cases. So we need journals and other mechanisms that actually start, and our peer reviewers and editors, to start influencing the way we present data to the community. As I said earlier, any sorts of diagram that most that get presented within presentations, papers, etc., emphasize the technology, the tools, etc. Very little around the domain-related expertise. It's great to see more of that actually being made a point of at this conference. So as we look at the data sets that we work with, what do we know? What do we know that we don't actually know? And then the really frightening part, what don't we know that we don't know? On top of which, when it comes to working with data, we cannot actually prove that something is there. We can disprove that some of what is there is not there, or isn't there, but we can't prove something as being present. We can make a good case for it likely to be there, but proving it is another thing. Some examples of what we do know in terms of this side of things. We can start defining the polygons we want to work with in domains in whatever sense, if we want to move that into a paleogeographic reconstruction. But the paradigm that typically comes up in mapping geology is that the youngest orogenic event defines the polygons. Well, in fact, when it comes to paleogeography, we've got to define what is the oldest block and where does that exist and how long back in time does it exist with subsequent overprints. If we look at the geochron data that we're talking of, this is just out of DateView, which is one of the databases that I've developed for IGCP. We can see that there are gaps there in terms of what's being captured. We know where those gaps are, but we don't know what's in those gaps. If we come down to other things like measures of how old the crust might have been, things like model ages from Samarium neodymium or Lutetium hafnium, the data sets are far more sparse. We're going to have to capture way more of what is out there to allow us to be more consistent and get better interpretations as we go forward. We can use things like ore deposits, again, in one of the other database systems here. This is just illustrating two of those, porphyry in red, green VMS. The VMS, they are very, very clearly characterized. We can use those as indicators of geodynamic setting. So it's what you win on one side, you use in the reverse direction as well. If you look at porphyries, you can age attribute those. That relates back to the tectonics. It tells you you're in the upper plate in a plated dynamic setting. So it's giving you very fundamental information of use in going through into the paleogeography. The other aspect that came out, that I feel has come out, is that we actually need to design databases on the assumption that other people are really going to want to use them and use them repeatedly by downloading data and being able to link the records in such a way that they can actually correct what has been changed in the master system or be able to find out what is new. in many of our database systems, we're not doing that at this stage. We need to make life easier for all of us. In terms of ore deposits, this is just a number of lead zinc type things. Looking through time, and effectively, we have this concept of supercontinents running back to Kenor land as one possible one back in the Archean, through Nuna, otherwise called Columbia, Rodinia, and Pangaea, Gondwana. You'll notice in here, Rodinia, a number of these deposits just don't occur. Why not? We need to try to understand part of the Earth processes that allow us to see through to that type of thing. We can bring in indicators of paleoclimate. If we want to model the blocks in terms of paleogeography, we've got to subdivide the polygons far more than we often do, and certainly way more than many of the Phanerozoic models currently do. This is a model that I've been involved in developing. You know, we're approaching 1,500 polygons at the moment, and that's not all breaking all the ones in the ocean into smaller polygons. That's essentially mostly crustal polygons with different ages as picked out. But you can reconstruct from that, in this case illustrating some of the paleoclimate type data back at 297 million at this point. You'll see the colors that go with that. As we go back in time into the Precambrian, one of the fundamental constraints is paleomagnetism. That's the distribution of locality information for where paleomagnetic data are available. Not to say it's good, that's what it is. The Precambrian, where we're talking of effectively 3,000 million years, that's the distribution of all the paleomag data, not the good data, all the paleomag data. We're looking at a couple of hundred. The way we represent maps at the moment, effectively, as at least in printed maps, and in fact into most of the GIS maps, is around showing what's the age of the different lithostratigraphic units. This here's one for the Arctic that I want to just use, because it's actually a very good compilation, because they add extra information in behind the scenes that the majority of geological maps don't. Instead of casting it in terms of time, if we want to work with it, we want some other attributes that we can then look at back in time. For instance, this, igneous rocks in red and purple. Blues are effectively marine, through to greens and yellows, not too much that you see there, are terrestrial ones, which means that when we go back in time, we can actually see the distribution of those as to where they occur. We can use that to try to understand and better delineate the processes we want to work with, on top of which we can layer other information. This here is just actually climate data, and I want to bring out the aspects. The first part of that was just looking at the temperature variations. You see the annual cycle. If you process that climate data at a per site level first, and then do other things with it, you can start seeing variations that relate to, is it hotter or colder than the average for that month back in time? And you can construct stuff that's actually way more useful in terms of understanding climate. But it requires the discipline-specific knowledge and a different approach to some of the data processing that's simply throwing it in to some of the typical big data type algorithms wouldn't allow you to do unless you pre-process that stuff in some way ahead of time. Other aspects of the data that come up, taking an example of what don't we know, or what don't we really know too well. If you take some of the geochemical data, a lot of stuff, you might show something as below detection. Well, at least then we know it's a very low concentration. On the other hand, if something is not analyzed, we don't have a clue what the concentration is. You'd be surprised at how much geochemical data out there just has blanks or zeros for what hasn't been measured or is below detection, at which point we don't know how to work with it. If we want to do the data mining on that, we've actually got to have a far better understanding of various of these data sets. If no matches are found, is it because there's no data there, or because there really is nothing that matches for the system? Have we even compiled the correct sort of attributes? this is a two-variable representation of what was actually a very small project. The reason I've raised it, and I'm not mentioning names as to who was involved in this, was a group of economic geologists got together with some data scientists in an exploratory data sense, trying to understand trying to distinguish between different styles of mineralization in a particular area. And amongst various variables, these were two that were measured, and the net result at the end was, well, if you go back and measure these, each of those colors is a different style of mineralization. So if we measure this type of variable, we can actually distinguish between them and project what goes forward. Try and discover something. Well, in fact, if you've worked with that particular isotope system, you know that the stuff on the left-hand side is just older than the stuff on the right-hand side. So you don't actually have to go and measure the isotopes in that one. You just have to look at the rocks with which they are associated, and you're on your way. A few more complexities than that as well. But they're capturing and using the wrong discipline knowledge, or a lack of discipline knowledge, in trying to solve problems. It worries me with big data that we might be doing a little bit too much of that in some cases, and that we're assuming that we're getting it right simply because it's big data. Some of the detrital side of things, Graham illustrated this type of thing earlier. We could recast that to try and get more information out of the data sets. Make it three-dimensional, in which we actually introduce the deposition age. Then color your probability diagrams where the highest peaks have some prominent color, like red in this case. Then go and look down on the top of that diagram, and effectively you produce a diagram somewhat like this. This is just split out for the different continents, taking a particular data set that was released earlier this year with over 400,000 analyses. So effectively, you've got your grain age on the bottom relative to your depositional age on the y-axis, and all of those red zones are where you've got lots of detrital ages of a particular age band. I've put in a couple of vertical bands here just to illustrate that there in Africa is obviously an intense period of activity that's been transferred into the detrital record. It doesn't quite match up, other than possibly in South America. There are subtleties in the information that we can use to understand things better, but we need to develop these alternative techniques that will allow us to visualize data better than we often are at present. We can also add in other overlays in that. So for instance, which of the grains in a particular data set are metamorphic? We can use thorium-uranium ratio in this particular example as a proxy. And we then start to see, well, this year, that's where the metamorphism back at, say, 1500, it only get transferred into the sediments around 500, I think it is. But what about that cluster there, where the metamorphic grains are coming almost instantaneously into the detrital sediments? That particular example happens to be associated with the Sulu eclogite grade subduction and metamorphism, very rapid uplift immediately after subduction and transfer into the sediments. We can use those as ways to get insight into data if we prepare the data better. We can even go on to some other classifications. Some of those dots are just for different interpretations. Spatial context really is important. And I'm going to finish off illustrating that in a moment. The other aspect is the variable uncertainty side. We really need to quantify and illustrate that. And as a community, we have to develop ways to show that better. We need to come up with better dissemination ways, acknowledge more of the discipline side of things. We need to allow for change in both space and time. And I'm just going to run a model here illustrating how we believe the Earth has changed for 1,800 million years. The colors on that, the continent, the block colors relate to present-day continents. Superimposed on top are dots, which relate to red igneous activity, so plutonic igneous activity, green is volcanic, blue is metamorphism, and then some grayish ones are effectively cooling ages. on top of which we have to deal with things like true polar wander. So, which is why the graticule, the blue lines, you'll see some massive changes at times. Some of the speed is obviously still wrong, and we're trying to address that as we push back in time. But when you're dealing with that amount of variability in space and time, we are fundamentally going to have to come up with rather different ways to dealing with some of the big data, the bigger data sets, that will allow us to work with situations much like this. And I'll let that run out if anyone has any questions. Thank you very much.
Thanks, Bruce. Is there anywhere we can see that?
Online or? It's actually, there's one very similar to that is actually online from last year's William Smith.
Oh, okay.
But it's something we're planning to publish later this year.